All right, welcome. In this video, we're going to talk about some of these practice problems involving both intermolecular forces and solutions. And so these are all released from old AP exams. So let's take a look at this one from the 2022 test first. And we're looking at two compounds right here. And the first question says, calculate the number of moles of NH2Cl present in 1 liter of a solution where the concentration is 0.016 grams per liter. So I like to kind of start by writing out things I know. So I know this is my concentration. A lot of times we're given concentration in molarity, but this time we're given it in grams per liter. So we're going to roll with that. And we also know we have 1 liter, and we're trying to find moles. That's the thing we're trying to find. So we know if we could figure out grams, we could find the moles, because I know what the molar mass is, 51.48 grams per mole. So what I'm seeing here is I have a grams per liter and I have a liter. So if I multiply these together, the liters are going to cancel. And so what that tells me is in my sample, I have 0.0016 grams of NH2Cl. And I'm trying to find moles. So I'm going to take my grams and I'm going to say, okay, there's 51.48 grams per every 1 mole of NH2Cl. So that ends up being 3.1 times 10 to the negative fifth. It's a very small number here, which makes sense because our amount of grams is very small. So I wrote that in scientific notation. I should have 2 sig figs in my response because this initial value only had 2 sig figs in it. And so this is really basically just a mole calculation problem, showing do we know how to go from grams to moles. Another way I could have written it is like this. I could have said it's 0.0016 grams divided by 51.48 grams per mole. That would be another acceptable way to write that out as well. All right, the next part of the question looks at solubility. So we're seeing NH2Cl is really soluble in water, whereas this one is nearly insoluble. And we want to explain this observation in terms of the intermolecular forces between each of the solutes in water. And so if I look at these substances by themselves, I can see that, oh, look, NH2Cl, it has some hydrogens that are capable of hydrogen bonding. And they're both polar, so they both have dipole-dipole forces, and they both have, dispersion forces as well. So if I was just looking at the molecule on its own, I'd say this molecule can hydrogen bond, but this molecule can't. But what's really important here is we're not talking about a substance alone. We're talking about this substance mixed with water. So that's going to kind of change some things here. So if we imagine, okay, how's this going to interact with water? It might help to actually just kind of sketch in some water molecules here. So this NH2Cl definitely can hydrogen bond with water. So this hydrogen can hydrogen bond. We also could have a hydrogen bond right here. So this has several spots where it can hydrogen bond. I'm going to erase this so I can draw it over here. So it can also hydrogen bond over here with the water. Over here, the chlorines can't be involved in the hydrogen bond, but a water over here, you see how this hydrogen in the water molecule is actually capable of hydrogen bonding. So what that means is when you stick this substance in water, this also can hydrogen bond with water. So both substances can hydrogen bond with water, which you might not see unless you try to draw it out. So it can be helpful to try and draw in some water molecules and try and picture how are they going to interact and is that possibly a hydrogen bond. The rule with a hydrogen bond is it's an H that's covalently bonded to an O-N or F, attracting to an O-N or F in a nearby molecule. So this still does count as a hydrogen bond right there between these two. So they both can hydrogen bond with water. They're both polar. They both have dipole attractions with water, but we can see that this one definitely can do more hydrogen bonding, right, than this one right here. So we want to say something about how the attraction, that this one has a stronger attraction to water. So if you look at the scoring guidelines for this one, according to the College Board, this is going to be a 2-point question. You got a point for identifying either that they both are capable of hydrogen bonding with water, or they also accepted that they both have dipole attractions with water. And then you got a point for saying something about the attraction between NH2Cl and water, that those IMFs are stronger than the IMFs between NCl3 and water. So whenever you have a question like this, make sure you identify what the intermolecular forces are, and then have some sort of explanatory statement comparing the strength of those IMFs. So if something is more soluble, that means it's going to have stronger IMFs with the solvent. And we can see that because it can hydrogen bond more. Okay. So that's a lot of time on that one question, but I thought it was kind of an interesting one, so I wanted to dig into that one. If you look down here, 2B is another solution one. We're seeing NH3 is very soluble in water, whereas pH3 is not. And I would, again, the question doesn't tell you to draw it out, but I find it helpful to draw out what this molecule looks like, and then imagine, okay, what happens, what's its interaction with water going to look like? So I'm going to draw the molecule, and I'm going to draw some water molecules next to it. And then I can see here that this right here, boom, 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 this is hydrogen bonding. This one right here, not hydrogen bonding. This one is ends up just being like a dipole-dipole attraction there. And because they both definitely look polar, they look a little asymmetric here. And so this one is going to have stronger attraction to water. When you're doing your explanation, it's really important to specify, when you're trying to explain solubility, you want to make sure you're discussing the attraction to water. So not just that NH3 can hydrogen bond, but that NH3 can hydrogen bond with water, whereas pH3 only has a dipole attraction to water. And so this attraction is stronger. So make sure you're discussing somewhere in your explanation that solvent, solute attraction. Okay, and the stronger this attraction is, the more likely it's going to dissolve. Let's look down here. This is a question that involves drawing things out here. So you want to show what happens when this lithium chloride crystal dissolves in water. So you want to recognize that this is an ionic compound. So when it dissolves in water, it's going to break apart into these individual ions. And they want us to show water molecules interacting. So this is our water. We know water is H2O. So these two guys are the H's, and this here is the oxygen. And we know that oxygen's more electronegative than hydrogen. So this side of the molecule is going to be negative. This side is going to be positive. So that's important because when you're lining up to your ions, you have the negative side of your water face the positive ion, and then vice versa. And then notice how these ions are not labeled, which is which. So we also have to figure out which ion is which in this crystal. And that's where we're going to use our knowledge about like periodic trends and just atomic structure. And if we look back on the periodic table and think about how cations get smaller and anions get bigger, we can identify that the small one is going to be lithium and the big one's going to be chloride. So that means when we draw it, we should show the water, when you're looking at the Mickey Mouse here, whoops, the oxygen side should face the positive ion there, and then the hydrogen side should face the negative ion there. So that's things you're looking for. And I think it told us we had to have one formula unit. So one formula unit, that means in this case, one lithium, one chlorine. So this is what we call a formula unit. It's the word we use other than molecule, because ionic compounds don't form molecules, so we have to have some sort of name. What do we call this? We call this a formula unit. And let's look at one more here. Dichloromethane has greater solubility in water than carbon tetrachloride. Account for this observation in terms of intermolecular forces between each of the solutes and water. So this is really key. Don't just say what IMFs the solute has, talk about what its attraction to water is. So we're looking at these ones. Carbon tetrachloride seems to be nonpolar. It's looking totally symmetric, right? That's how we can identify polarity easily. And then this one is dichloromethane is asymmetric, so this is polar. And if we imagine what's going on here with the polar, well, let's look at this one first. So if we have water molecules here, this attraction here between carbon tetrachloride and water is going to be a dispersion attraction. So because if you're a nonpolar, the biggest IMF you can experience is dispersion, right? So that's a dispersion attraction between carbon tetrachloride and water, whereas dichloromethane is polar, so it can have dipole attractions with water. So if we draw that out, like the hydrogen side of water would attract to the chlorines. So the chlorine's more electronegative. So this side of the molecule is going to be negative, this side is going to be positive, and then over here. And notice how we can't have any hydrogen bonding here because these H's are not capable of hydrogen bonding because they're bonded to a carbon. So there's no hydrogen bonding, but they are polar, so it will have dipole forces. So let me label this. This one has dipole forces. This one's just dispersion. So the reason why dichloromethane is more soluble is you want to say something about how, you know, the dichlor has dipole attractions to water, which are stronger than the carbon tetrachloride's dispersion attraction to water. And just, you know, if you check the, you know, scoring guidelines to this question, I'm pretty sure they will. Yeah, they talk about this, well, a couple of notes I should say. Dispersion forces, another term you use for dispersion forces is LDF. So LDF stands for London dispersion forces. So if you see LDF somewhere, that's what that means. You might also hear this described, this specific scenario is something called dipole-induced dipole. And that happens when you have a molecule that is polar and a molecule that is non-polar. It's something that doesn't show up on, like, in our textbook, you know, lists of IMFs or anything like that, but you might see it kind of pop up sometimes in some College Board references. So you don't have to call it dipole-induced dipole, but it's technically a little bit more accurate. So if one of the molecules is polar, one's non-polar, that's going to maybe be a little stronger attraction than just between two non-polar molecules. So just FYI, if you see that terminology, it has to do with, it's between a polar and a non-polar. But it's totally fine to also just say carbon tetrachloride has dispersion attractions to water. That's totally fine too. So if this is like confusing you, ignore what I just said. Okay. So that's a little bit there. Actually, while we're here, let's talk about number 5 as well. So we've got, this is another example where I think it's helpful to draw it out here. So we've got a test tube. Over here we have water, which we know, you know, water is polar. And then we've got C6H14. That looks pretty, that's like carbons with a bunch of H's around it. That is very symmetric. That looks pretty non-polar. So basically when you have just a hydrocarbon, like a bunch of carbons with a bunch of hydrogens around it, they're going to be non-polar pretty much always. And we also can see they don't mix. That's another clue that this is probably non-polar. Okay, so you got a layer that's non-polar, a layer that's polar, and then you add iodine to it. So if you look at iodine, it looks like this. So this looks totally symmetric. So iodine is going to be non-polar as well. And iodine is, let's see, it tells us somewhere that iodine is purple. That's key. So iodine is purple. And then we add some iodine here into this and mix it up, and we observe that this solution becomes purple, whereas this solution stays clear. So we want to explain this. So basically what we're noticing is, what we want to try and explain is, why does iodine, you know, dissolve in hexane? I don't think they named it here. This is hexane though, but not water. Really, that's what the question's asking us. So again, this kind of scenario, if there's lots of words, sometimes I find it helpful to draw out a picture for myself of what is happening. And so you want to talk about the relative strengths of interactions between iodine and the various, you know, solvents there. And so so if you're thinking about the interactions here, we're dissolving iodine in hexane. Hexane experiences dispersion forces. So does iodine, and then iodine and hexane experience dispersion forces with each other. So it's relatively easy for iodine to get in there and mix in with your hexane because all their IMFs are the same. So dispersion forces, they tend to mix pretty well. In order for iodine to mix with the water, it would actually have to break those water molecules apart from each other, and water molecules are experiencing hydrogen bonding. And the water molecules, so let me write that out. The water-water attraction, so the solvent-solvent attraction is hydrogen bonding, which is very strong. And it's much stronger than the attraction of water to iodine, which is just dispersion forces. So we'll observe that the iodine does not dissolve in water because this attraction between water and iodine is not sufficient to overcome water's attraction to itself. Whereas the attraction of iodine and hexane are like fairly similar. They're all dispersion forces, so iodine can mix together with hexane a little bit easier. And if you're looking back at the scoring guidelines, just so you know for this question, there is a point just for kind of understanding what's happening in a scenario and acknowledging that, look, iodine's dissolving in hexane and not in water, so they got a point just for doing that. And then you got a point for referencing the differences between how hexane and water interact with iodine. So again, you want to make sure you're in these types of questions with solubility that you're referencing at some point the attraction between the solvent and the solute, right? In this case, if you're trying to explain why something doesn't dissolve, it's useful to compare this attraction to the attraction of the solvent to itself. That's why the iodine does not dissolve in water, is because this attraction is much weaker than water's attraction to other water molecules. And you can see the scoring guidelines for all of these ones in OneNote. I just want to try and also explain it in with some visuals as well and talk through it. So let me know what other questions you might have, and thanks for watching.